Okay, so the next problem is entropy generation during a throttling process. Okay, so we know, and this is how our device looks like, a throttling valve, okay, and the steam at 7 megapascal and 450 degrees C is throttled in a valve to a pressure, so inlet conditions are given and exit pressure is given, okay, 3 megapascal during a steady flow process. Okay, determine entropy generated per unit mass, so it asks the lowercase s, okay, during this process, and check if the increase of entropy principle is satisfied. Okay, so it asks me the lowercase s, the s and the not actually entropy generated. So lowercase s generated entropy. So I can have it in my energy, the entropy balance equation, right? Okay, let's start with writing the energy balance, the entropy balance equation. Okay, so here is your entropy balance equation that is valid for every problem. So it's easy to start you with this balance and look how you can figure out what is asked in the question. And in this case, basically what we can say is, since the problem says steady flow, okay, this term goes to 0. Okay, so let's write it down then. What type of entropies are getting in? So is there any heat interaction? No. In those cases where we have throttling system, we assume the heat and work interactions are 0. And there is no work done anyhow, and the fluid flows fast enough to prevent heat interactions. Therefore, since entropy only carried with heat and the mass, in this case we don't have heat, so it should be carried with the mass. So the mass is getting in, and instead of basically capital S dot, you can write lowercase m dot times the lowercase s. This will give you, remember that's how we do it, right? So this is entropy per mass times the mass flow rate should be the total entropy flow rate. Okay, so instead of in this equation, instead of writing capital S dot, I can write m dot times a lowercase s1, signifying the inlet entropy. Okay, so what is getting out? What entropy is getting out? It's minus mass times exit entropy. Remember, in the mass balance of these steady flow systems, the inlet mass has to be equal to, remember, inlet mass has to be equal to exit mass and equal to a constant mass flow rate. So what happens here is then the mass is the same in the exit and the inlet, and the entropy is changing though, okay? And plus this generation term is equal to 0. Okay, if you rearrange it, keep the generation of entropy rate on the left hand side, then on the right hand side you can arrange it within a parenthesis like that. Okay. Now, the problem was asking us the lowercase entropy generation, right? So see, entropy generated per unit mass, so it's asking the lowercase s. So in this case, in this problem, I don't know mass flow rate, but I can cancel it. I can divide each term with the mass flow rate. Okay, and this goes, and this becomes basically S capital S over mass flow rate becomes the lowercase s. Okay, so therefore on the left hand side we have lowercase s entropy generated is equal to S2 minus S1. Okay, so then if you want to figure this term, which is asked by the question, figure it out. In order to do that, you need to figure out the inlet and exit entropies. Okay. So how are we going to do that? To be able to figure out the entropies, all you need to do is look at the tables. That's what you do, okay? Because the two pressure and temperature is given to me, you can directly figure, since the problem tells us it's steam. Okay, you can look at the steam tables, or you can first look at the saturation tables to show that it's actually a superheated vapor. Then look at the table A6 and read the enthalpy and entropy values from the table under these conditions. Okay, remember, it is important to read entropy and enthalpy here at the same time, because first we need entropies for the solving the problem. And why do we need enthalpy is because in a throttling valve, if you remember, the inlet enthalpy was equal to exit enthalpy, and this condition is important for us because in the actual pressure of the exit, which is given to you, you need another property to be able to look at the tables and figure out the entropy. Okay, so now the pressure is given. You know, for the throttling valve, it is the enthalpy that is inlet and exit is equal, and you already know the inlet enthalpy, so it should give you the exit enthalpy. Those are the same thing. So now you have pressure and enthalpy value. From that you can look at the tables again and figure out the entropy in the second case, in the exit. Now you calculated that, you subtract those values from each other, and you get the entropy generation per unit mass.